Hi, I'm Ming, and this is Kitchen Matters. We're a team of material science grad students helping you explore the mysteries of food. In this video, we're discussing the science of tempering chocolate. Now, I personally think this is a really interesting topic that touches on many of my favorite ideas in material science. So let's get into it and really understand what tempering means. In our video on the crystal structures of chocolate, we established that chocolate is primarily made of cocoa butter and cocoa solids. We also know that the molecules in cocoa butter can arrange themselves to form 6 different crystal structures, also referred to as phases 1 through 6. These phases have different melting points. Phase 1 has the lowest melting point and phase 6 has the highest. Of these 6 phases, phase 5 cocoa butter is the most desirable because the melting point is just around body temperature. That means phase 5 chocolate stays solid in your hand but melts in your mouth. In fact, the chocolate we buy at the store mainly contains phase 5 cocoa butter and very little of the other phases. That brings us to where we last left off. To make these chocolate bars in the factory, all of the ingredients are first melted down in a big tank because liquid chocolate can be molded into different shapes. Then the molten chocolate is carefully cooled, during which the cocoa butter starts to nucleate or it begins to form crystals. These little crystals that form are also called seed crystals. Just like a small seed grows into a larger plant, these little seed crystals grow into larger crystals. And once we have enough seed crystals, the chocolate can be poured into a mold to finish cooling. Those seed crystals will grow until all the chocolate is fully solidified. The goal of chocolate makers is to cool the chocolate so that only phase 5 seed crystals form, and none of the other phases. How do they do this? Through a careful process of cooling and heating called tempering. The idea of tempering is not unique to chocolate. In fact, blacksmiths have been tempering metals for centuries, carefully heating and cooling them to achieve the desired microstructure. Today we'll learn how to be culinary blacksmiths and temper chocolate. Let's think about this cooling process using a graph. On my graph, I'm going to have the temperature of the chocolate on the y-axis and the time on the x-axis. I'm also going to draw 6 horizontal lines that correspond to the melting points of each phase of cocoa butter, just for our reference. We start by heating everything up to around 45 degrees Celsius so that all the chocolate is fully melted. Since this temperature is above the melting point of all 6 phases, no crystals can form and the chocolate stays liquid. Let's just imagine what would happen if we cool the chocolate down to room temperature and kept it at 25 degrees Celsius. We're still above the melting points of phases 1, 2, and 3, so we won't expect to see any phase 1, 2, or 3 crystals. However, 25 degrees Celsius is below the melting point of the other phases, and therefore we'll see those crystals start to form or nucleate. Over time, those crystals will grow, and we'd eventually observe a mixture of different crystals. Note that phase 6 chocolate is generally much slower to nucleate than the others, so we can effectively ignore it for the purpose of this video. Now, I'm sure you've noticed that this product is not what we want. We've ended up with chocolate that contains a mixture of crystals, whereas we really just want phase 5. So here's a question for you. What if, instead of cooling the chocolate down to room temperature, we cooled it to some different temperature instead? What might be an appropriate temperature to cool the liquid chocolate down to make sure that only phase 5 crystals form and not any of the others? Remember that you can effectively ignore phase 6 chocolate. Hopefully you picked a temperature in this range, between the melting points of phases 4 and 5. If we cool the chocolate down to 31 degrees Celsius, for example, this temperature would be above the melting point of phases 1 through 4, so only phase 5 crystals would form. And there you have it. At its core, this is the basic idea of tempering, picking the right temperature to achieve the right crystal structure. But wait, it's never quite so simple. Even though cooling to 31 degrees Celsius would get us a reasonably pure product, it turns out that it takes a long time for enough phase 5 crystals to nucleate at this temperature, potentially even several hours. Chocolate makers use 2 main strategies to make phase 5 crystals form more quickly. The first strategy is called undercooling, and the second is called seeding. Let's start with undercooling. In general, the further you cool a liquid down below the melting point, the faster crystals will form. Therefore, a common approach to make phase 5 crystals form more quickly is to undercool, which means cooling further below the melting point. The more you cool, the greater the drive for the molecules to nucleate instead of staying in a liquid. In fact, it's common to cool liquid chocolate down to around 27 degrees Celsius or so. Since the temperature is lower, crystals nucleate faster. Now you're probably seeing that there's a problem with this approach. In the process of undercooling to make phase 5 crystals form faster, we've now put ourselves in the temperature range where phase 4 crystals can also nucleate. Not to worry, because now we're going to heat the chocolate back up to around 31 degrees Celsius again. In doing so, we're now back above the melting point of phase 4 chocolate, so any phase 4 seed crystals that nucleated earlier will melt away. However, we're still below the melting point of phase 5 chocolate, so those crystals stay. By doing this clever undercooling and heating process, we managed to nucleate phase 5 crystals more quickly than we would have had we stayed at 31 degrees Celsius the whole time. At this point, the chocolate can be poured into a mold and gently cooled, allowing the nucleated crystals to grow until all the chocolate is fully solid. This entire process is called tempering chocolate, and you can see that it's very finicky because you have to be at a very precise temperature all the way through. If you, for example, accidentally overheat the chocolate and overshoot, you might end up melting all the phase 5 crystals too, and you'd be right back where you started. But wait, there's a second way to make this process go even faster called seeding. Currently, we're relying on the cocoa butter molecules to just nucleate all by themselves when they just so happen to bump into each other in the right way to make a crystal. This type of nucleation is called homogeneous nucleation, and it's quite slow. One trick to make phase 5 crystals form more quickly is to give them some help by stirring in some pieces of solid chocolate, which already contain phase 5 crystals in them. These phase 5 crystals already present in the chocolate chunks act as additional seed crystals. Think of these as a template or scaffolding that the molecules can attach to, allowing the crystals to form faster. This process of nucleating on the chocolate chunks is called heterogeneous nucleation, and it's faster than homogeneous nucleation. If you're thinking this feels a bit circular, you're totally right. We're using phase 5 crystals to make more phase 5 crystals. That's the nature of seeding. Tempering chocolate isn't something that just professionals do. It's something that you can do in your own kitchen too. Let's say you have a chocolate bar lying around that you want to turn into edible art, like a chocolate shard to go on a dessert. Let's do a quick review of this entire tempering process from start to finish, this time focusing on how to do it in your kitchen. First, chop up the chocolate bar you want to temper. We'll put 2/3 of it into a warm glass bowl to melt, and save the other third to use as seed crystals later. And yes, my glass bowl is almost comically too large, but it's the only one I own. After all the chocolate has melted, we now undercool to around 27 degrees Celsius. Stir constantly and monitor the temperature. Even though we can't see them yet, there are small crystals beginning to nucleate in the bowl. Whilst we're cooling, we can now add our reserved chocolate chunks. These will not only help the chocolate to cool faster, but they'll also act as seed crystals for heterogeneous nucleation, allowing phase 5 crystals to form faster. Now that we've cooled down to 27 degrees Celsius, the phase 5 crystals have nucleated, but some phase 4 crystals may have formed too. Now we heat to 31 degrees Celsius to melt any phase 4 crystals, leaving just phase 5 behind. Remember to stir constantly, and take the chocolate off the heat once you reach 31 degrees Celsius, so you don't accidentally melt the phase 5 crystals too. Finally, you can pour this mixture onto wax paper or some other non-stick surface, and leave it to rest until all the chocolate is solidified. During the resting period, those small seed crystals that were formed can grow until eventually all the chocolate becomes solid. Now, crystal growth happens much faster than nucleation. Now that we've seeded phase 5 crystals, they'll grow much faster than new crystals will nucleate. Therefore, we don't have to worry about other phases forming during this cooling period. After a while, I now have a thin sheet of tempered chocolate that I can cut into the shapes I want. See how the product is nice and shiny with a good snap, and that's characteristic of phase 5 chocolate. Of course, I didn't have to go through the trouble of tempering the chocolate. I could have just melted the chocolate bar and cooled it straight down to room temperature. But as we saw at the beginning, that would have led us to chocolate that contained a mixture of phases, not just phase 5. For comparison, here's some chocolate I made by just directly cooling to room temperature, and you can see it doesn't have the same snap or shine as the tempered chocolate did. In contrast, when I temper the chocolate correctly, I end up with the right crystal structure, which gives me the properties and performance that I'm after. Now that you're a master of tempering, go forth and try this in your own kitchen. We'd love for you to play around like a material scientist would. What happens if you change the temperature, cooling rate, or amount of seed crystals? You're now ready to be a kitchen blacksmith.